using spare space in worker nodes and desktop disk to build a gLite storage element, a presentation for the demo session of the EGEE 5th User Forum.
Hello, my name is Francisco Brasileiro. I am here to present the work on distributed file system that has been developed in the Distributed System Lab of the Federal University of Campina Grande in Brazil. This is a joint work with my students Thiago Pereira, Jonhnny Silva, Carla Araújo and Alexandro Soares. In this demo, we'll show how the BeeFS file system has been used to build gLite storage elements that are able to aggregate the spare disk space in both desktops and worker nodes of a gLite computing elements connected in a local area network. We also show how this storage element can speed up the processing of data-intensive parallel applications. The BeeHive file system, or BeeFS for short, is a fully POSIX-compliant file system that stores files in the spare disk space of machines connected by a local area network. It has a hybrid architecture that works as follows. Metadata information about the files is stored in a dedicated centralized server named the Queen Bee server. The actual data is stored in several storage servers named honeycombs, distributed in the machines connected by the local area network. A Honeybee client implements the POSIX interface that allows applications to access files without needing to bother where these files are located. To access a file, the Honeybee client contacts the Queen Bee server to discover where the file is located. As described before, the Queen Bee server stores the metadata associated to the files. One of these metadata is the location of the replicas of each file. The Queen Bee server checks if the client has the appropriate permissions to access the file and, in case of success, returns the address of the honeycomb server that stores the primary replica of the file that's being opened. With this information, the Honeybee directly contacts the appropriate honeycomb server to access the data. A clever file placement policy makes it highly likely that the read and write operations are executed on a honeycomb that runs on the same machine where the Honeybee client runs, making data access very efficient and scalable. Since BeeFS is fully POSIX compliant, it is trivial to expose a BeeFS file system as a gLite storage element. Two common deployment configurations are the following. Harvest the spare disk space of shared desktops computers connected in a local area network, and another would do similar thing with the spare disk space of worker nodes of a gLite computing element implemented by a dedicated cluster. An added value of a storage element based on BeeFS is the possibility of executing data-intensive applications in a much more efficient way. Let us see this in practice with an example application. The application uses a face detection algorithm to process a number of photos that are stored in the backend file system. We compare the execution time of the application over the same set of input files in two scenarios. One that uses BeeFS as the storage backend and another that uses NFS, the state-of-practice centralized file system for local area networks. The applications are started at the same time and each uses half of the processing power of a dedicated cluster. Both the NFS server and the BeeFS Queen Bee server run on the same machine. The BeeFS file system uses the spare disk space of the cluster nodes where the application executes. Honeybee clients and NFS clients are installed in the appropriate machines. The demo configuration is the following. The application receives as input a list of files that contain the images. Each image can be processed in parallel. Upon detecting the face in the image, each independent execution of the application outputs a new image with the face highlighted with a red circle. In the execution machine, two executions of the applications are started at the same time. They use a MapReduce-like engine that tries to send the computations to the machine that is closest to the data that needs to be processed. In the NFS case, since the data is stored in the NFS server, this is of no use and all data is read via the network. On the other hand, for the BeeFS system, this makes a huge difference, since almost all file system operations are executed without using the network. As we will shortly see, this configuration yields a much more efficient execution. The visualization machine runs a program that shows a window with all the input images and then keeps inspect the file system to see if outputs have been produced. Whenever a new output is spotted, the input image is replaced by the output image with the face detected. 2 of such windows are displayed, one for each file system backend used. Let us see this in action. We start by simultaneously launching the execution of the application in the 2 scenarios. The execution machines start to send jobs to the cluster machines, while the visualization machine starts the graphical interface with the NFS in the top and the BeeFS in the bottom. We now advance the time to the point that the first output starts to be generated, which for this experiment happened after 1.5 minutes were elapsed. It is interesting to notice that the scenario with the NFS appears to be executing faster than the one with BeeFS. However, a few seconds later, the scenario for BeeFS starts to produce the outputs and completes its execution much sooner. The fast startup phenomenon is explained by the fact that not all jobs have the same processing time. Jobs are scheduled randomly, and the NFS scenario ended up starting to execute the shortest job first, while in the BeeFS scenario the largest jobs were started first. Using BeeFS to set up a gLite storage element is not only a good way to harvest idle storage resources, but is also an enabler of many data-intensive applications. More information about the BeeFS file system can be found at our website. You can also contact us via email and we'll be happy to help you to start to use BeeFS. Thanks for your attention.